So, today I am going to finish discussion on arc furnace steel making, and in the context of arc furnace steel making, today I would like to talk a little bit about stainless steel making. So, yesterday I told you that arc furnace is used mostly as a melting and refining unit, and if you have to make alloy steels, then the primary steel making vessel need not be used. And this is a classic example where we will see that we will mostly refine, will mostly melt the scrap in an electric arc furnace, and then the melt is going to be transferred into a separate reactor where decarburization as well as alloying will take place. So, yesterday I gave you some idea about the making of ball bearing steel, particularly after the refining, melting and refining period in arc furnace, and in the ladle in presence of inert gas stirring, I have shown how one can add high carbon ferrochrome, substituting a little bit of low carbon ferrochrome in order to make the process of making ball bearing steel attractive and economic. And I think I looked at the literature and I found that the high carbon ferrochrome is about and low carbon ferrochrome is 3 times more expensive, and vis-a-vis you will see that carbon steel can go from 750 to 800 US dollar per ton. So, that is, so you can imagine that if you want to use low carbon ferrochrome. So, LC, this is LC ferrochrome, low carbon ferrochrome, this is HC high carbon ferrochrome, this is carbon steel. So, there is quite a bit of that. You have chromium loss also. The slag will contain some amount of chromium, you will not be able to recover the entire amount of chromium because it tends to undergo oxidation. So, therefore, to circumvent such losses, the efforts are made to use high carbon ferrochrome, and I think this price table clearly points out the decisive advantage that high carbon ferrochrome can offer in terms of better process economics. Now, stainless steel, as you know, that stainless steel does not corrode or rust. So, it has an excellent anti corrosion or anti rusting property, and it has found tremendous application over the years in diverse engineering applications, be it starting from utensils in our homes to medical instruments to railway wagons and car components, because these are stainless steel tends to be anti corrosive. So, even they are more expensive because stainless steel, as we will see, will contain chromium and nickel, not always though. If it contains chromium and nickel, we call the chromium based stainless steel as a 300 series stainless steel. On the other hand, if you have manganese based stainless steel, then also it is a 200 series stainless steel. There are 400 series stainless steel also, and so on and so forth, and there are diverse chemical composition, and what we see in our daily life is a variety of steel, which stainless steel, which we call as an austenitic stainless steel. Okay, and there are, I think, beautiful artifacts made out of stainless steel, like beach chairs, in top class hotels in Europe. You will find that stainless steel structures as chairs put up with Italian leathers. Okay, and over the years you have developed technology to make stainless steel paper thin also, so that it can be rolled and it can be shaped very easily, so that one can lift the chair. The thickness of the components, steel components, needs to be very small in order to be lightweight, because steel as such has very high density. So, similarly, today if you go to many houses in North America, you will find that the kitchen cabinets are no more made out of wood, because there is an embargo on chopping off trees to fulfill our needs, because this planet is suffocating from various kinds of toxic gases, and the plants provide a good respite, that you all know. So, because of that, there is an increasing tendency for having the entire kitchen cabinets made out of stainless steel, and there is a decisive advantage as well. In such a case, the stainless steel cabinets used to last lifelong. On the other hand, woods do undergo some kind of a degradation and some kind of an attack from insects, etc. So, global stainless steel production, we know that global steel production is about 1.5 billion ton. Stainless steel production is not that much, but it is catching up. We find even in India, you will find in many places that the chairs, etc., for example, where large number of people wait in railway stations or in bus stations, today the chairs are all made out of stainless steel, because of their durability. Once you invest a little bit more money, they last perhaps forever. So, global production is I think hovering around 50 million ton. That is the kind of figure that I have in my resources, which may be a little bit old, and India produces somewhere around I think between 3 to 4 million tons per annum. That is our, and it is projected that stainless steel is going to come in a big way, and as we become more and more developed and financially progressing, then in that case we will find that more and more artifacts are going to be made out of stainless steel. Today railway compartments are not made out of stainless steel in India, but these are not far off when we will have railway compartments, and there is already a move. Of course, we do see toilets, etc., components of it made out of stainless steel, but even the gross structure of the railway bogies or compartments will be made out of stainless steel. So, this is expected to go up tremendously, and therefore, there are many new units have come up producing stainless steel. For example, Jindals have started a plant in Jajpur in Odisha, which has more than a couple of million tons of stainless steel production. There are other companies like Biraj Ispat near Bombay, which produces stainless steel. Mukund also does produce stainless steel, and there are many other small organizations, but it is going to catch up, and days are not far off when we will see maybe by the time we have 300 million ton or 250 million ton by 2030, we will also see stainless steel catching up to 10 million ton for sure. So, how is stainless steel made? For example, stainless steel will be made mostly from stainless steel scraps. Okay, a good part of the charge is going to be stainless steel scrap, and stainless steel contains, as we see, if you are talking of this stainless steel is not so good. Most of the time, just it is out of context here a little bit, you may have seen that there are many stainless steel artifacts, particularly the kitchen utensils, which tend to develop cracks, and those are from 200 series, where nickel is replaced by manganese, and the deep drawing quality of the material suffers as a result. So, this is a cheaper variety, and as the content of nickel increases, we only talk 18-8 austenitic stainless steel, which is 18 is chromium, 8 is nickel, but there are diverse grades. You can get nickel as much as 24%, and these are going to be very, very expensive, excellent and outstanding quality of stainless steel. Okay, but this is what we see mostly in good in terms of good kitchen utensils, etc. So, austenitic stainless steel, and of course, cheaper varieties, this one which is also available in the market, and if you buy it, you should be prepared that they may not last as long as the austenitic stainless steel does. So, chromium and nickel, and we know if you look at chromium and nickel, we have classified nickel as a non-oxidizable elements under steel making conditions. So, that means if you do a nickel balance, that nickel contained in scrap will be exactly equal to or more or less equal to nickel in the at melt down in the melt itself. Okay. So, conservation of nickel you do not have to, you can recover the 100% of nickel, but this is not true with chromium. Okay. So, chromium is trying to partition. So, chromium comes under the third category, where we say that it is a partially oxidizable elements. It is not a completely oxidizable element. So, chromium will oxidize, get into slag, and some chromium will tend to retain. So, recovery of chromium is not going to be 100% from stainless steel scrap, it is going to be less than 100%. So, therefore, we have to have a nickel source which is to be applied, because at the end we may not make 100 tons of stainless steel from 100 tons of scrap of stainless steel. Okay? That is perhaps not possible because of loss of chromium, etc., and loss of iron also during oxidation. Apart from chromium and nickel, we have carbon, but that carbon content is this is the what percentage of carbon in stainless steel. Typically, all stainless steels contain very low amount of carbon, because the simple fact that chromium is a strong carbide forming element. So, you can have during the solid state reaction precipitation of chromium carbide at the grain boundaries, okay, particularly during the solidification process. And you have an ultra low carbon stainless steel also, which is a premium product, and that ultra low carbon one is talking about. So, this is less than 0.8% carbon, and this is less than 0.02. So, this is ultra low carbon stainless steel. And when you have, for example, low carbon stainless, carbon of the level of 0.8, you use a process called duplexing process. And when you use this ultra low carbon, you have a triplexing process. There are 3 reactors connected in series which operates, and here it is the EAF, which is used as a meltdown unit, and then we have an AOD, argon oxygen decarburization, and here you have 3 reactors working in series, AOD and then VOD, vacuum oxygen decarburization. So, from 0.08 to 0.02, that removal carbon driving out carbon at that particular level will necessitate that you have a reactor where there is vacuum to reduce the carbon monoxide partial pressure, and therefore, these 3 reactors are. So, that is how the name is derived. 2 reactors working in conjunction is duplexing, and 3 reactors is triplexing. Now, so for making of stainless steel, 300 series stainless steel, we would say that the raw material would be stainless steel scrap. This is one part of the raw material. Then we have, because chromium is going to be partitioned, we require a chromium source. So, we will use high carbon chromium, high carbon ferrochrome. Okay. We can use plain carbon scrap also, plain carbon scrap. And if we use all these things, we will understand, the volume is now more. So, the stainless steel, the amount of nickel which is contained in this charged material will not be enough. So, we have to use primary nickels. So, we have this is, I think, not manganese nickel, this is chromium nickel, chromium manganese. There may be so, primary nickel is going to be necessary, okay, because this nickel is going to be replenishing the nickel deficit, which will originate because plain carbon scrap will increase the volume of melt, and because we have stainless steel scrap, only part of the charge, and high carbon ferrochrome does not have any nickel. So, therefore, the total volume that you are going to produce will not give you 8% nickel, it is going to be substantially less, and therefore, the primary nickel will be required. And we know that nickel possibly, nickel does not undergo any oxidation. So, nickel can be added in the form of just nickel shots, pure nickel shots towards the end of, we have to just ensure that the nickel melts and disperses or mixes homogeneously in the system. So, basically during the meltdown period, these three materials are going to be used. And this high carbon ferrochrome, for example, can contain carbon to the extent of 6 to 7%. So, there is going to be lot of carbon in the melt. Stainless steel of course will not contain much carbon scrap, it will contain chromium and nickel. A plain carbon scrap may contain some amount of carbon, but this high carbon ferrochrome is going to contain an enormous amount of carbon. So, in order to achieve the target carbon chemistry, what we require now is to remove carbon. Now, removal of carbon, so the charge contains at meltdown charge will contain at meltdown chromium, some nickel and possibly some other kinds of impurities also, phosphorus, silicon, etc., which may come out from the plain carbon scrap. So, these are, by the way. So, the moment in electric arc furnace, so you can melt, and this is the melt composition, melt down so chromium is going to be less than 18%, nickel is going to be less than 8% and carbon is going to be significantly higher than 0.08%. And I must say again that I write values, and in a course like iron and steel making you cannot have one single value. What I write is a representative value that you must remember. For example, hot metal composition, whatever I have written, the price ranges that I quote, because these all tend to fluctuate. Composition will fluctuate from one plant to another plant, the price will fluctuate. If you listen to my lecture after 3 years or 4 years, whatever price I am quoting will no more is going to be valid. Similarly, the amount of steel which is being produced, what I am quoting today is not going to be tenable after a few years or so on. So, what I am quoting is a the values, the numerical values that I am writing basically are representative values valid at this point of time that you must remember. So, now once you have melted by application of electrical arc energy. So, the arc furnace there is no refining per se, okay? There is no oxygen lancing, there is no refining. So, arc furnace is going to be used for making of and basically what happens is typically the special steel plants which contain arc furnaces, okay? So, it is there the arc furnace sometimes when there is a gap between the two heats, okay, the arc furnace, the same arc furnace can be used just to melt down without have to carry out any refining operation. So, stainless steel, many special steels also produce stainless steels. So, in between production of various kinds of steels, steel grades, one single grade of stainless steel, one heat of stainless steel can be made where the stainless arc furnace where maybe no slag is necessary, and one can no slag is to be produced or generated or made artificially, and there you can just melt it and then transfer the melt into what is known as an AOD converter, argon oxygen decarbonization converter. So, it is under argon and oxygen that decarbonization is going to take place, and as I have indicated that at meltdown the carbon concentration, because of the use of high carbon ferrochrome, and we are using high carbon ferrochrome, I hope that point is clear to you, because of economics or economic reasons. So, therefore, we have to drive out carbon, and if you want to drive out carbon, you remember that you will put in oxygen, that is oxygen here, that oxygen will react with carbon, but note that chromium is also a partially oxidizable element. So, chromium can also react with oxygen. Let us quickly see that how does the free energy of formation with respect to delta G naught T, and then the free energy, this is carbon carbon monoxide line, carbon carbon monoxide line, and this is chromium oxide line. And what is this temperature? This temperature is about approximately 1800 degrees centigrade, 200 degrees centigrade higher than steel making temperature. What does this indicate? This indicates that above 1800 degree centigrade, the free energy of formation, and these are all done with respect to, they may not be in toto applicable to steel making, because here this is carbon monoxide pressure, total pressure is 1 atmosphere. Similarly, chromium oxide, the oxide phase is in the pure stage. On the other hand, unless and until the slag is saturated with chromium oxide, we really cannot consider the slag or the chromium oxide activity to be unity, or chromium oxide to be in the pure phase, but nonetheless they give us good guidance. So, this indicates that carbon monoxide is relatively more stable than chromium oxide above 1800 degree centigrade. So, that means, if the temperature is more than 1800 degree centigrade, if you have oxygen available to react with a chromium atom or a carbon atom, oxygen is going to now preferentially go to carbon, because at that temperature chromium oxide has much more stability and the free energy of formation is smaller than the free energy of formation of chromium oxide. So, therefore, if you have a mixture which contains carbon and chromium, you require that the temperature must be quite high. At 1600 degrees centigrade, you will not be able to remove. So, your objective is to preferentially oxidize carbon over chromium, but that may not be entirely possible, because such a high temperature is not easy to generate. So, the reaction, and chromium is a transition metal. So, we can have chromium oxide, the lower oxides as well as upper oxides. So, we can write chromic oxide just like ferric oxides, and this is in slag, and then if you write carbon in the melt, and then we have carbon monoxide, and then we have chromium in the metal. So, what does this indicate? This indicates this is dissolved, carbon is dissolved in metal, chromium oxide is there in the slag, and this essentially indicates that if the reaction goes in the forward direction, if you can drive the reaction in the forward direction, the purpose is fulfilled, that we will have lesser amount of chromium oxide in the slag and more amount of chromium will be win back in the metal itself. And this will tell us that yes, if driving this equation in the forward direction essentially implies that oxygen will be carbon will take up the oxygen rather than chromium. If any chromium takes up the oxygen, which will nevertheless happen, but carbon, if it meets that chromium oxide, will be able to take back the oxygen and in terms become oxidized and carbon monoxide. So, that we want this reaction in stainless steel making to go into the forward direction. Now, so therefore, it is understood that we have to have, for example, if you look at the thermodynamics of this reaction, that we have lower the pressure of carbon monoxide in the system, better will be the tendency for this reaction to go into the forward direction. And lower carbon monoxide pressure essentially indicates that we have argon oxygen decarburization. Now, when you put in argon, then the gas contains what? The gas bubble contains, and the bubble rises through the liquid. The converter looks like more or less the similar converter. It has a argon, nitrogen, oxygen, and you have a top lance here, and this lance does not blow at the same rate as a basic oxygen converter. There is no supersonic jet here, and we know that oxygen transfer is very, very poor from the top, because in the absence of an emulsion phase, because this is not a good combination as far as starting in the system is concerned. So, this side blown basically side blowing facility basically helps to provide the stirring in the system. When you blow in argon and oxygen together, what happens is the bubbles which rise through the liquid, this bubble will contain not only oxygen, but they will also contain some amount of argon in it, and the total pressure will be dictated by the pressure of all the gaseous phases itself. So, argon, as you can see, will have a dilution effect on the partial pressure, whatever may be the total pressure, the very presence of argon within the bubble, at the interface of this bubble only, because oxygen is available there, and there is the carbon oxygen reaction which is taking place. Okay, and so you can, the carbon monoxide bubble which forms at the melt gas interface, okay, that will necessarily in the presence of argon give rise to a much lower pressure, as opposed to the case where we do not have any argon. Okay. So, this is called the dilution effect, actually dilution effect of CO in the system. If you can somehow pick up a bubble, hypothetically speaking, and analyze it, you will find that the proportion of carbon monoxide is much lesser. On the other hand, in the absence of argon, if you pick up a bubble, you will find that the proportion of carbon monoxide in that is going to be much smaller. So, injection of argon into the system allows us to maintain a lower pressure. So, we have been able to create a favorable condition for this reaction to go from left to right. Thermodynamically, we have seen that higher temperature is needed. So, a high temperature like 1800 degrees centigrade will also cause this reaction to go from the left to the right. The third thing is that this reaction will be facilitated for a given concentration of Cr3O4. The activity coefficient of Cr3O4 in the slag is going to be very, very important parameter. The activity will gives us as an indication that if the activity coefficient is low, that means the compound is very, very stable in the slag phase itself. It will be very difficult to eliminate or drive out that element. On the other hand, if the activity coefficient is extremely high, okay, in that case we can expect that the species has a great tendency to, it is not very comfortable in the slag, it is not very stable in the slag. So, it is looking for an avenue to go out of the slag phase itself. Because this is a basic oxide, by the rule of chemistry we can say that a high basic slag which will contain large proportion of calcium oxide, etc., will increase the activity coefficient of Cr3O4, because there are two basic oxides, strong basic oxides cannot, because CaO is more powerful. So, in the presence of CaO, calcium, all the silica, etc., will be eaten up by calcium oxide, and this guy will have no chance to react with other acidic compounds, and therefore, it will be left with no option but to look for a different avenue to go out of the slag phase itself. So, therefore, that this driving this reaction in the forward direction or the desirable direction, which amounts to winning more metal in the chromium, or which amounts to preventing the oxidation of chromium in the relative oxidation of chromium to carbon, we require three conditions: dilution by argon as it is done in the AOD converter, number 2 high temperature, and number 3 a high basic slag. Now, this here the tap to tap time is basically quite long, because the side blown converters are also, the gas is injected, this top lancing oxygen does not really, is not a good way. So, the stirring is not so appreciable in this particular system, despite the fact that you have a side blown, one side blown what you call tuer through which oxygen. So, it finds preferentially the gas is going to be leaving through something like this. This is the path of the gas which will, so this part virtually will have very little amount of stirring, and the top jet, the transfer of momentum from the gas jet to the metal is also not very appreciable in such systems, which can cause stirring, that we have seen in the case of POF. So, the system is not very well starred, okay? That is one limitation, and that is why even though you have carried out melting elsewhere, the rate of carbon oxygen reaction is not appreciable, decarbonization rates are not quite appreciable, because you do not create a very large interfacial area, you do not create a very large velocity in the system, which are essential condition for achieving higher decarbonization rate. So, as a result of which the tap to tap time here could be quite long, in comparison to, for example, the basic oxygen steel making converters. Even making 45, 30 to 50 tons of steel may take 70 minutes, 80 minutes, 90 minutes of processing in the converter, and at that long time, basically what happens is you cannot really use low carbon ferrochrome, because then you have to have a lot of carbon. That carbon is going to oxidize, produce heat, and this has to make the process really autogenous. Okay. So, therefore, we have a basic slag which is prepared here, okay. And then you blow oxygen from the top, argon or nitrogen on oxygen from the bottom, and as a result of which this reaction takes place. Parallelly, there could be many other reactions. Carbon can react with oxygen, okay. This is also there, iron is there. If you are injecting oxygen, this will also form, the slag will also contain FeO and so on and so forth. Okay. There are various other reactions which is possible. If there are silica contained in the plain carbon scrap, that silica is going to be, we will see silicon is there, we will see what is the source of silicon, because you may be wondering that sir has shown that silicon in first 3 minutes is removed totally, and then how come the silicon comes in the plain carbon scrap, and that will be clear to you when we will talk about deoxidation towards the later part of this lecture. Okay. So, therefore, many reactions are going to take place. These reactions are heterogeneous chemical reactions, and as we know that they are going to be dependent on interfacial area as well as the prevalent velocity fields, and that is why the efficiency of steel making is not as high as it is in the case of BOF steel making or cube of process. Now, during the process itself, as you can see here, that even though I have said that 3 conditions are necessary to drive this reaction in the forward direction. So, the slag can contain not only calcium oxide, not only FeO, not only some traces of silica, for example, this could be very small actually. Okay. It can also contain chromium oxide also, because 100% chromium you will not be able to win back. There is going to be, because the efficiency, as I said, that the chemical efficiency is not so high in the system, and therefore, the slag will also contain some amount of Cr2O3 and other oxidizable elements. If you have aluminum also in steel, as a result of deoxidation, that alumina can also go, phosphorus if it is there, that will also go as phosphates and so on and so forth. So, there could be this slag, because of the presence of chromium oxide, the slag has, as opposed to the steel making slag, which is a little bit blackish in color, okay, this has a greenish appearance, and so therefore, one should be able to look at the color of the slag and then say that how much of chromium oxide is really there in the slag itself. Now, before you tap the furnace, it is often desired that you will try to win back, if there is quite a bit of even 3 to 4% or 5% of chromium present in the slag, try to win back, or if there is quite a bit of Cr3O4 left in the slag, in that case you can also say Cr3O4, there is no problem. Then you will like to, for better economics, you will like to win back the material. So, now the slag, it is an oxidizing slag as of now, okay, as you are doing it in argon AOD converter. Okay. From the moment you started to blow the oxygen and you stop oxygen blowing into the system, okay, it is an oxidizable slag that is present here. It contains iron oxide, because you are blowing, you are decarburizing and you are blowing oxygen into the system. The moment you have stopped blowing oxygen into the system, now what happens is this oxidizable, if you want to get back this chromium from the slag to the metal, then you have to convert this oxidizing slag into reducing slag. Okay. So, therefore, but you cannot add carbon, Okay. So, to win back chromium which is present, let us say Cr2O3, which is present in the slag, you will either add silicon and then or add aluminum, which will remove all the oxides. Aluminum can reduce FeO, aluminum can reduce SiO2, aluminum can reduce Cr2O3. Okay. If there is a silicon there, similarly if silicon you add, silica is more stable than FeO, silica is more stable than Cr2O3. So, the moment you have added silicon into the melt, Okay. So, what happens, the moment you put pure silicon, the silicon will not dissolve in slag, the silicon, solid silicon will progressively dissolve in melt, and then this reaction will start, and then the slag metal reaction will take place and silica and chromium will be. So, the winning back of chromium is, as I have shown here, through this particular reaction. Okay. So, you can write a slash here, or aluminum also if you can add, then you can get the same kind of a reaction. Instead of silica you are going to get alumina. Okay. Winning back of chromium from the slag phase by addition of silica essentially requires that, essentially falls in the category that you are converting the oxidizing slag into a reducing slag. If you remember, I said you cannot throw away the slag, okay, or prepare a fresh slag. Your objective is to, during the oxidation process, as you have eliminated all the carbon, some residual chromium oxide is sitting in the slag, and you want to get back that from the slag into the metal. And in order to facilitate that, you have added silicon. The silicon does not dissolve in slag, silicon dissolves in metal, and then the metal in the slag. So, you add silicon, you do, and again this is an exothermic reaction, because the bond strength of silicon to oxygen is much stronger than the bond strength between oxygen to chromium. So, that will also produce some amount of heat. So, the moment you add silicon, okay, you have to stir it vigorously, because you require good slag metal resistance, and since already you have a basic slag, therefore, the silica is going to be taken up by the slag, and where the silica activity coefficient is going to be extremely small, essentially indicating that you have stable silica in presence of CO or calcium silicate formation in the system. You will not see free silica at all, or silicon with high silica with high activity. So, this is a classic example of oxidizing slag converted into a reducing slag, and you have to, because the slag, whenever the slag will have some commercial value and it contains an element which is also there in the melt, if you can do something to win back that particular species from the slag phase itself, it is going to give you, decisive advantages. So, in the process of this high temperature process and using the dilution effect with argon, you can get to 0.1% carbon, 0.08%, 0.07% carbon, no problem, but getting below that is going to be really difficult. And under that case, what happens is that once you deslag, once you win back the chromium, deslag it, then the melt, which is there, which contains now maybe it is stainless steel, it is 0.8% or 0.7% carbon, and you want to produce what you call ultra low carbon stainless steel, and then you can take the melt from the AOD into what is known as the vacuum oxygen decarbonization. So, here what happens is you will be lancing oxygen in limited quantity into the melt, and you will also be heating. Okay. So, that is the the metal is going to be tapped into a ladle, the ladle will be there will be gas stirring, and the entire thing is going to be put into, and then you have a lance through which you will have. So, you will have argon stirring there on the ladle, you will have stainless steel from AOD, stainless steel from AOD. It is sort of a tank degassing arrangement. So, you have, we will study that, vacuum, and through this we will put in oxygen as well as argon. Okay. And you will have some amount of carbon oxidation here. So, you will have to have adequate temperature, so that because you already have, now that you have eliminated carbon with respect to chromium, you do not really require much higher temperature, because you have already created enormously high temperature in order to achieve preferential oxidation of carbon over chromium. So, the melt temperature is very high, and your steel casting temperature could be about 1560 degrees centigrade, 1570 degrees centigrade. So, there is a good margin of temperature. So, the loss of temperature is not a very important issue in this context, and therefore, additional heating is not necessary at this particular stage. So, if you can just put in oxygen because there is vacuum. So, what happens is that you have this reaction, dissolved carbon reacts with dissolved oxygen, and you have now a vacuum pressure could be about 10 to the power 1 millibar or so. That is the pressure you can apply. So, that means virtually CO concentration is 0 in the gas phase, and as a result of which what happens is there is a tendency for this reaction to further go reducing the carbon from its 0.8% or 7% level to about 0.2% level. So, the vacuum treatment would be necessary, and unless a vacuum treatment you cannot reach this kind of a carbon content. And this tells us that ultra low carbon steel is going to be substantially more expensive than the stainless steel. Stainless steel as such is more expensive than carbon steel, and ultra low carbon stainless steel is going to be even more expensive because you are talking of beyond AOD another processing. So, you have to have a capital expenditure, you have to have spent some time on a daily basis, and so on and so forth. So, this is what it is. So, I do not want to discuss anything beyond this as far as stainless steel making is concerned. Okay. We can now move on to a new topic. And so, we have made the steel is made in whether it is stainless steel or carbon steel in primary steel making vessel. So, the next step is that we want to now take out this steel from the primary steel making vessel and make this steel making unit furnace or the converter available for the next heat. Okay. And then we have to take out, and that operation is the tapping operation. And tapping is done mostly in a cylindrical shaped vessel. That vessel is called a ladle. It is marginally tapered. It is actually, you can say that is the kind of a geometry. Two to 5 degrees taper is there at the bottom. Okay. This is a refractory lined vessel, basic refractory, tart dolomite as well as magnesite bricks. So, tapping is going to be done in a preheated ladle, because otherwise there is going to be significant drop in temperature. As such, there is going to be drop. So, we have a furnace here. So, this is my basic oxygen furnace, for example. I would say okay, so this is so that is the way the converter looks like. Okay. And then we have a tapping. So, we have molten metal here, and then we have slag here. So, that's how it is. And the molten metal comes out at what rate? Maybe 7 tons, 10 tons, 15 tons per minute. That is the rate at which molten metal is drained out. And as this goes down, there is a chance that this is the steel making or oxidizing slag. And we have the ladle sitting here, and that is how the tapping operation done. So, these holes remains closed. So, it is the same thing. If you have an electric arc furnace, So, you have an EBT, so you tilt the furnace and then the ladle sits there and the molten metal. Now, this ladle, so therefore, it can have typically the converter size and the ladle capacity, they are more or less identical. We will try to see that whatever the amount of the steel which is being made, we should be able to, because there is one chemistry. So, we would like to put it in one ladle and not two ladles. Okay. So, there is one-to-one correspondence between the capacity of the ladle and the capacity of the steel making furnace. These are preheated because otherwise they will absorb a lot of heat and the molten metal will be a significant drop in molten. As such, when because of air entrainment or the radiation heat loss from the surface, this is maybe 1600 degree and you have heat loss according to Stephen's law as 1873 raised to the power 4. Huge radiation loss takes place. So, during the tapping itself, there could be 60 to 70 degree drop in tapping temperature, delta T, that is very common. And also because of the fact that we have nitrogen, so there could be quite a bit of nitrogen absorption by the liquid steel. Nitrogen has great solubility in steel, about I think at 1600 degree centigrade about 500 ppm of nitrogen gets dissolved in steel. Okay. Hydrogen is about 28 ppm, nitrogen is about 500 ppm, I think 470 exactly. Of course, it is a function of again chemistry. If you have a nitrogen forming element present in steel, then of course, the solubility is going to be much larger. And oxygen solubility, pure oxygen solubility in iron is about 2000 parts per million. So, oxygen as such will not get transferred from the atmosphere because of the simple fact that the melt contains already great amount of oxygen. Okay. Oxygen, dissolved oxygen, as we have seen that we have been able to eliminate carbon in primary steel making vessels, silicon, etc., but the price we have paid is that there is quite a bit of dissolved oxygen. It will vary from process to process, 300 to 600 ppm of oxygen, and the final oxygen required most of the time would be 10 to 20 ppm. That is our final and the product nobody is going to buy because they will give rise to blowholes, etc., porosity in the casting. So, therefore, from 600 level, 600 ppm level, we have to get it down, and that the metal contains already 600 ppm of oxygen. There is not much oxygen which gets transferred from the atmosphere, and as a result of which, what happens? The melt chemistry undergoes changes here, particularly with respect to nitrogen content and with respect to temperature. Also, there is a drop in temperature itself. So, that is why this drop is taken into account, that we want to have 1610 degrees, 1590 degrees centigrade around that time of the furnace temperature. So, it is around 1600 or plus minus 10 degrees will be the temperature, tapping temperature, in order to accommodate for the temperature drop in the system. As tapping goes on, the molten metal bath here is going to be rising as a function. So, the stream is coming from the furnace, that is the stream. Okay. This is A and this is also A, that is the stream, entering the ladle and then gradually it is filling up. Okay. As the ladle is hot, and initially what happens is the ladle is filled up with some material like slag forming agents. We want to make now our synthetic slag. Okay. So, we will use a known amount of, depends on how much basicity we want. We can use some silica, we can use some Al2O3, take care, help from phase diagram in order to ensure that we get a liquid, the proportions are adjusted in such a way that we get liquid slag. Okay. And then we in the empty ladle itself, these compounds are already added. Okay. And when the molten metal comes from the furnace, and the kinetic energy could be very large, okay, because of the drop, and this distance from here, the ladle itself could be 3 meter depth, and this itself could be the exposed length above the ladle top could be another 3 meters or 5 meters. So, this is, that means the steel is falling from a height of 7 to 8 meters from the base of the ladle itself. So, it is with enormous amount of kinetic energy, and as I said 10 tons per minute is the rate. So, you can imagine the momentum that is going to bring in here, and that momentum is going to create a huge amount of churning action in the ladle itself, expediting all those elements expediting the melting and dissolution and reaction of all those elements we have added. So, in no time itself, a slag is going to form and the slag is going to be floating on the free surface itself. This slag is very important for us, this synthetically prepared, because it protects heat loss from the system, because otherwise heat will be radiating during the process of heat radiation is proportional to absolute temperature raised to the power 4 as per Stephen's law. And then what happens is, once the ladle is completely filled, then all ladles are fitted with a gas injection device, because the processing is not yet over. We have to drive out oxygen, and maybe the temperature has gone down, some nitrogen has come, we have to remove nitrogen. So, further processing we anticipate are there. We have made only crude steel, this is not to be delivered to the customer. Okay. So, a set of processing will come, and that there is no scope for heating the material chemically. It cannot be made autogenous, because we have driven out carbon, we have driven out silicon from the hot metal itself. It therefore understood that we may have to heat the molten material or molten steel with an additional heating source, so as to satisfy the thermal requirements of the downstream processes. So, we will have heat and mass transfer taking place in the subsequent stages. So, there is going to be a provision. So, the moment the furnace is tapped, tapping starts, the argon blowing is also started. So, there is a huge amount of stirring which goes on, which expedites melting, slag is formed, and then after some time what happens is that the ladle is ready to be taken. During the time of pouring of the molten metal, once the ladle slag is formed and the metal is half filled, it is at that time deoxidizer elements are added. The elements which have greater affinity towards oxygen and which will help us to remove this oxygen, reduce this oxygen, they are also added, and we want to take advantage of this intensity of stirring. You may have noted that when you open a tap in a bucket in a bathroom, how much of stirring really that kinetic energy of the jet, water jet generates within, and it is the same kind of a scenario, but relatively the momentum and the density of steel is large, and hence at a large rate of 10 tons per minute, you can imagine the intensity of stirring. So, if you add deoxidizers, their melting and dissolution is going to be very rapid, and they will be available to react with oxygen, or the deoxidation reaction rate is going to be extremely fast, and that is why the deoxidizers are added, and they are going to be added close to the vicinity of the tapping stream where the maximum velocity really exists. So, once deoxidation takes place, elements are added, stirring is continued, we will put back the ladle with a cover, and then the ladle will be shipped for subsequent processing operations. So, the stirring will continue, and on a railway track these ladles will be moving from what is known from a tapping station or from the BOF melt shop to the LRF ladle refining furnace station. Some people say LR treatment station, that is also there. During the process of tapping, one important thing we have to note, that we should not allow any slag to get into the ladle, because this slag contains FeO, and how much FeO? As I have indicated, 20 to 25% FeO. So, therefore, the slag, if it comes here and if you add deoxidizer elements, that deoxidizer elements is going to be eaten up by the slag, and so your objective was to add deoxidizer to take care of this oxygen, but no, it is not happening. When you have carryover slag, this is called the carryover slag. The presence of carryover slag in the ladle is detrimental, as we will see, and we know now for economic reasons, because the deoxidizer will be eaten up by the slag rather than dissolving into the melt, but more importantly, as we will see later on, this will tend to make steel extremely dirty or full of oxide inclusions. So, therefore, there are slag detection systems which are available to us today. They give us a signal the moment slag comes. There are darts, for example, there are materials which are floating at the slag metal interface, because they have density close to slag metal interface, and they tend to move towards the nozzle, and the moment the slag layer level comes down, approaches that of the nozzle discharge plane here, and then what happens, this dart really sits on closing the hole itself, or there are electromagnetic and thermal imaging techniques also which are available, which allow us to cut down the moment we know that slag is coming in, we raise the converter, and then there is not a single drop of additional metal or slag which can come into the system. And in this way, it is possible for us today to ensure that the slag thus formed with the addition of the new species contains less than 0.1% FeO, virtually cutting off the slag itself. So, the ladle is now ready. We have added deoxidizer elements, and we have to now study that how does the deoxidizer elements react with this, what are those deoxidizer elements and how do they react with that, what is the rate of the reactions, and so on and so forth. So, this is a very important step, and this has a huge bearing on the economics of the steel making process, and this is what we are going to discuss in the next lecture.